All right, so oh, there it is. This right here is supposed to be a depiction of a sound wave being produced. So I'm at some location right here. So imagine there's a still lake and I throw a rock and it goes right in the middle and these waves form. So this red line right here should be the waves that have sort of rippled out. And then later on in time, this is still supposed to be a circle, as was pointed out earlier. It's supposed to be a circle that's this first wave right here that's now gotten that big. At some time later, after a period, I throw a second rock right smack dab into the middle of the exact same spot. Okay, some more for that one to work. There we go. Nope. And so the second wave is formed, and that's what this blue circle is. So we have these two waves, and then you throw another one in the exact same spot, and we just basically get these certain waves being formed. Since the waves will be traveling at a certain speed based upon the properties of the water, that there's a certain wavelength here, and it should be the exact same wavelength there if I throw the stones into the pond in the exact same spot at the exact same amount of time. So if there's a bug over here on the water, it's basically going to get hit by a wave, and then it'll be hit by another wave at a period later, then hit by another wave after a period later, and so on. So now, instead of throwing the rock into the exact same spot, we're going to throw it into a different spot. So that's the exact same spot, so that first one now, that first wave is now out to there, and the second one, we're going to throw the rock slightly off. That second rock is now here. So the source of the wave is moving. And by the way, today's free food is glazed carrots.
Yum.
What am I don't like them? So that red wave is now still centered on my dotted line right there. Closer to a circle. The blue wave is centered here. So if you look at basically the wavefronts, these wavefronts are much closer to each other than those are. Unlike over there, ideally, they would be the same length. So if you're a bug on the water over here, you're going to be hit by these waves more frequently. If you're over here, you're going to be hit less frequently. If this is sound, being hit by the waves more frequently means you hear a higher frequency or a higher pitch. Now, Hewitt does go into differentiating between pitch and frequency. I use them interchangeably. That's just, if you wish to maintain distance between those two and say that they are not the same thing, pitch is what we hear, frequency is the property of the wave, fine, but I would probably still use them interchangeably. So you're hit more frequently. From a sound point of view, it's a higher frequency. Except over here, you're hit less frequently, it's a lower frequency. And so as the something is coming towards you, you will hear a higher frequency and then it's something going away. That's in essence the Doppler effect. So car goes by, it's the higher frequency when it comes towards you, the lower frequency when it goes away. And now a video which demonstrates it, which apparently some countries have a problem with.
You have a problem with the video?
This or the next video, it's hard to tell which one they have more of a problem with. Because you can see which videos were banned by certain countries. I think Pakistan banned the video the class video where I showed this. And there were a couple others.
Wait, this is your video?
No.
Oh.
The video of class when I showed this video or the next video, one of them got it banned, got my video, the class video banned in certain countries.
Interesting achievement.
because physics is dangerous. Ooh. I'm gonna try it when no one's watching. Can you see that well enough?
I think you have subtitles on. Not sure if you want them on or not.
I'll leave them on. Sound?
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up and bunch.
So what I was trying to draw on the board, so you can see that they're much closer to each other here than here. So shorter wavelength, higher frequency, bigger wavelength, lower frequency. If this is also related to something I did earlier when we're talking about sound, these black lines here would represent the high pressure, or the high pressure in between would represent the low pressure of sound.
Is it same speed though? Is the speed the same though?
Once the wave is released, the speed of the wave is based upon the medium that it's going through, not based upon the source.
Okay.
Wait, you said the shorter is what?
Shorter wavelength, higher frequency.
Okay, vice versa.
Yeah, and from the point of view of just thinking about the word frequency, if I'm over here, because the wavelengths are bunched together, I'm gonna be hit by waves more frequently, so higher frequency.
Behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you, and the car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant, distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Does the redshift have anything to do with eclipses? Does the redshift have anything to do with eclipses?
With eclipses? No. Though we didn't really talk about, well, it's actually used more, radar guns also use it. because they're sending electromagnetic waves at a car, and then the car bounces the waves back. And so the difference between what's sent out and what comes back tells you how fast the car's going. Eclipses is just pure, the sun gets blocked, or the moon gets blocked, depends on if it's a lunar eclipse or solar eclipse. And you talk about the fact that during the lunar eclipse, it looks, I guess, the blood moon.
It looks like red.
Yeah, that's, light basically comes in all sorts of colors, and if it's all blended together, we see it as white light. When it enters the atmosphere or is going around an object, the stuff that bends the easiest is the lower energy stuff, the red light, as opposed to the blue. And so that's why we see the red, is that the blue light doesn't bend as much, so this is the source. You know, the blue light is more apt to go like that, and the red light is going to bend more. That's where that comes from. And there's one other. That is not what I wanted. Right, so similar to what we were just seeing right there, this one's traveling closer to the speed of sound. So they're bunched up much more dramatically here. Again, the waves are traveling at the speed of sound, and the object here is getting close to it. Now, if it actually goes to the speed of sound, we got this second one down here. And you get this huge bunch up of waves right here. Now remember, these waves, that 440 hertz that I played earlier, that's 440 waves per second. And so even though it's more, you don't see the 440 waves here because it would just look like a blur, this right here at the very front, where they're all bunched on top of each other, is a huge high pressure wave because you get this incredible constructive interference. And whatever is creating the sound at that moment is undergoing incredible buffering from the sound that it's producing, on top of sound, on top of sound. And so when they were first trying to break the speed of sound in airplanes, this is the point that planes typically would fall apart. And then if you exceed the speed of sound, you get this. So it produces a sound and is traveling in front of the wave. You get this crest right here where you get the constructive interference. And so you get this cone. So if you're on the ground here and the wave is something going faster than the speed of sound, you get hit by this very large pressure wave. And I mean, you would definitely hear it. Now, it is possible to break the sound barrier with a whip. And when you use a whip, sort of gets off this one. So with a whip, in essence, you've got a long handle right here, and then you've got string attached to it out here, or string's not the right word, but you've got the whip part out there. Now with the handle, the longer the handle, the more torque you have, because remember, I'm applying a force here, which ultimately gets translated to a force up, to a torque about my hand up here. Or if I If I'm doing it like this, the torque about this point right here. So it basically gives me a longer moment arm. The downside is the longer the moment arm is, that means the more moment of inertia is in the rod part, and it makes getting to the sound harder. Now, the string, or the width part of it, tapers off. Now, the tapering, if you think back to the formula, it was the tension divided by the linear density. So as the width tapers off, it's getting smaller and smaller, my linear density is decreasing. As my linear density decreases, the speed increases. When I get to the free end, basically the tip of the string is basically going to double in speed, because it's going to go from up here to down there incredibly quickly. So if I get the wave going at 200 meters per second, by the time it gets to the tip's going to go 400 meters a second. So, which is breaking the sound barrier. And so all I have to do when doing a whip is to get it to the point where the speed gets faster and faster and faster. As long as I am at least half the speed of sound, we'll get that crack and create a sonic boom. So there's that. And then, I think you've seen this part already, but notice I did talk about relative sound between the two. Now, the examples that have been given so far have been the source moving, but the observer moving also. Let's have the source stay still and the observer move towards them. So we have sound waves being given off. I guess there is no, oh, there's pause down there. So sound waves are being given off. The wavelength of the waves isn't changing coming from the source, but the observer is hitting them more frequently because the observer is heading towards it. So the observer is going to hit it and then hit the next one. They're basically going to meet each other. And so the observer will be hearing a higher frequency because he's hitting the wavelengths more frequently.
If the observer is moving at a constant speed, will the frequency, it won't be the same as what's actually being given out, but will the frequency be consistent? And then if the observer were accelerating, the frequency be higher?
Sorry, ask it again.
If the observer were moving at a constant speed, would the frequency be the same in the eyes of the observer, not the actual frequency? But if the observer was accelerating, would the frequency be higher?
Accelerate as in speeding up.
Yeah.
If the observer sped up as he went, then the frequency would keep increasing.
Yeah. Okay.
And the observer, if you work through the math, if the observer is heading towards the source at 80 meters per second, that's one frequency, but if the source is moving towards the observer at 80 meters per second and the observer is standing still, it's actually going to be a different frequency that's being heard. It doesn't matter which one is moving. And the math bears that out, but beyond the scope of 110. But there's a video on there. And then YouTube. Doing a shift here for just a second. Even in this little clip right here, notice the node. This middle part's not shaking as much as the sides are. And then you've got the antinodes. Probably technically the antinode is off here, but we do have a node here.
Interesting that it's in the middle of the bridge.
Yeah. Well, we'll get into it then. I don't think that's the one I wanted to show. But it might be.
And it was just wind that did that, right?
Yep.
Adam.
only pay for what you need.
Liberty, 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 liberty.
Is it like a shill?